First, I would like to thank the organizers for giving me the opportunity of talking about this in this conference. Okay, my work is mainly in quantum mechanics application of geometry and symmetries in quantum mechanics. But I think that the results we obtained for scalar tachyonic fields are interesting, so I decided to present in this nice meeting of Lorentzian geometry. It has a long story from Benalmádena, starting in Benalmádena until now. Okay, so my presentation, since all the papers which are based on, and also my papers are mainly focused in quantum mechanics, but I will try just to give a geometric representation, a pictorial geometric representation. So, well, this is the content of my talk. Okay, the motivation, since the paper by Feinberg in 1967, sorry, where he introduced the possibility of the faster than light particles. Well, there were previous works, but he gave us the more complete presentation of faster than light particles, and he coined the term tachyon, which from the Greek means fast particles, to mean particles that travel faster than light. Okay. But the problem is that since this paper was introduced, it was seen that the existence of these particles, which are allowed by special relativity, by the equation of special relativity, there are a lot of inconsistencies, mainly due to violation of causality. So there have been hundreds, thousands of papers devoted to these problems. So the system of tachyon particles are very, very controversial. In fact, they are believed not to exist. However, the concept of tachyonic fields, oh, sorry for the mistake here. The tachyonic fields, which they are also named tachyons, so they produce a bit of a misunderstanding. But they are fields, not particles, because they are solution of Klein-Gordon equation for m squared, for negative square mass. So these tachyonic fields are well defined, and I mean it's also a bit controversial, but it's assumed that information does not travel faster than light with tachyonic fields, or at least when you quantize a tachyonic field, the fluctuation of this tachyonic field, the particles of this tachyonic field are not faster than light. Okay? So this is the difference between the tachyon particles and tachyonic fields. Okay. Okay. In this talk, we shall discuss a result we obtained recently, introducing a relativistically invariant scalar product for classical scalar tachyonic fields in Minkowski spacetime. We have in mind to generalize to other spacetime like the sitter, but for the moment we have done for Minkowski spacetime. Okay, from now on, I will for tachyons I will mean a tachyonic field. Okay, and if I am talking about tachyon particles, I will mention explicitly. So I will talk about tachyonic fields. Okay. If we consider Klein-Gordon equation, there are two. Well, there are the Klein-Gordon equation is the Casimir, the eigenvalue equation for the Casimir, one of the Casimir of the Poincaré group, of the Poincaré algebra. So this eigenvalue, which will be the D'Alembertian, that is this part, can have a positive, negative, or zero values. So positive values correspond to ordinary solution that do not violate causality, ordinary solutions with the positive square mass, and they are called usual particles. Also, to distinguish from tachyons, they are called tardions. But this is not a very well name, but in the literature you can find this word for ordinary particles, ordinary fields, solution of Klein-Gordon equation with m squared positive. But there are other solutions where you have here minus sign, and these are tachyons. The other solution with zero will correspond to photons, okay, particles without mass. Okay. Even though the equations are very similar, and there is only a small difference in signs, the fields, the associated field, the solution to this equation are drastically different. Okay. In addition, we have seen that solution of the tachyon equation, Klein-Gordon equation for tachyons, are more similar to solution of Helmholtz equation, which is this one in optics, than the solution for the Tardions equation. Okay, so there are very tachyons are more similar to fields which are solution of Helmholtz equation than fields who have solution to ordinary Klein-Gordon equation. Okay, we will see this. Okay, so let's review Helmholtz equation. Helmholtz equation is an elliptic equation which appears in optics, appears when one considers Maxwell equation, which is the equation for propagation of electromagnetic field, and we restrict to monochromatic solution, to monochromatic fields, and then the derivative with respect to time disappears, and we have this constant which is related to the frequency of the electromagnetic wave. So this is an elliptic equation because we'll have the Laplacian, and the Cauchy problem is well known that for elliptic PDS is not well posed in general. So we cannot specify the initial data in a hyperplane or in a screen if we are in 3 dimensions in a screen, and this we will not provide a solution, a unique solution, and a stable solution for the Helmholtz equation. However, has been proved that if we restrict to oscillatory solutions of the Helmholtz equation, then the Cauchy problem is well posed. Oscillatory solution means solution which essentially exponential with imaginary exponentials, because the problem is that you can consider real exponentials, and they are in fact solutions of Helmholtz equation. But the problem is that they or decay exponentially or they grow exponentially. So the problem is not well posed for them. So for oscillatory solution, the Cauchy problem is well posed. In addition, it was shown by Steinberg and Wolf in 81, and after we studied this problem in 2020, that you can find a positive definite Hermitian inner product for solution for the Cauchy data on a Cauchy surface, which usually is a screen if we are considering in 3 dimensions, a plane, which is the screen, and with the data which I denote in this way. This is the values of the field at the screen, and these are the values of the normal derivative at the screen. Okay, with this Cauchy data, we can introduce an inner product which is non-local, in the sense that involves in this case a convolution kernel. So it's a double integral with a convolution kernel. Okay, this is the setting. We have the screen, which is the Cauchy hypersurface in this case, the Cauchy data here, and this is the normal direction, and this is the solution of Helmholtz equation. They are fields, oscillatory fields, and these are the wavefronts for the fields. And at each point of the hypersurface, the screen, the possible values of the momentum, which are the frequencies in the Fourier decomposition, they are restricted to lie in a sphere, because the velocity of light is constant. So all possible values of the momentum have norm norm 1, or if you take c equal to 1. So all possible values of the momentum lie in a sphere. If the wave propagates in the forward direction, it will be only the forward half hemisphere. But in general, any solution will have a momentum in a complete sphere. Okay. So in this case, the Fourier components of the field will lie in a sphere, and we need the two halves of the sphere, the two hemispheres, to describe a complete solution. We cannot take only one half of the sphere. We need both of them. So since the sphere is non-trivial topologically, it will require two charts, and we need both charts to describe an arbitrary solution of the Helmholtz equation. Okay, since the Fourier components of the solutions of Helmholtz equation lie in a compact set, they are delocalized in the sense that we cannot construct arbitrarily localized solutions of Helmholtz equation. In fact, in the screen, the Cauchy data cannot be localized. Okay. In fact, the most localized solution we can construct are beams, and even in this case, they have a finite width on the screen, and of course they spread on the propagation. The width is the size of the spot that we can see on the screen. So all solutions will only have a finite spot, cannot be a point. They will be all spots. Okay. So these are the features of solution of Helmholtz equation. Okay, we'll consider Klein-Gordon equation in Minkowski space-time for tachyons, for ordinary particles. Okay, in this case, the Cauchy problem is well-defined, it's well-posed, because so there is no restriction of the solution space. Okay, so also all solutions with real frequencies you consider they are oscillatory. Okay, and we can also construct a positive definite emission in a product which is in this case is local, and which involves the values of the function of the Cauchy surface, upper surface, and the values of the normal derivatives of the upper surface. We normally will take this Cauchy surface, for instance, the t equal x0 equal to 0. This is the usual one. But we can take any other which is obtained by Lorentz transformation of this one. Okay, and we obtain a positive definite emission in a product if we restrict to positive energy solution of Klein-Gordon equation, because here we can have, in fact, the Fourier components, the momentum, which are the Fourier components of any solution, will lie in a two-sheet hyperbolic, and there is one here and the other below, but we can restrict to the one which is in the future, pointing to the future, which is inside the light cone. Okay, so we can restrict to them because they are two separated, sheeted, and they are one of them is invariant and the Poincaré group. So we can restrict to one of them, and restricting to one of them, we obtain a positive definite inner product which is local. Okay. Okay, this is commenting. Okay. Okay. The other thing is that if we consider the projection onto the Cauchy hypersurface, sorry, or the momentums, they cover the whole. I mean, the whole hypersurface, so they are not restricted. In the case, I forgot to mention, in the case of Helmholtz equation, the projection of the momentum, they lie on a disk. If we are considering a screen, they lie on a disk, so they are compact. In this case, they cover the whole R3, and then they are unrestricted. So the spatial components of the momentum are unrestricted, and therefore Cauchy data can be localized. So in this case, we can have localized solutions at the Cauchy hypersurface that will evolve in time. Okay, for tachyons, we also have an hyperbolic equation, but we have minus sign here, and this makes that the Cauchy problem for the Klein-Gordon equation for tachyons is not well posed, because we also can have even for real spatial components of the momentum, we can have non-oscillatory, we can have exponential solutions. So we have to restrict to oscillatory solutions, and in this case, the Cauchy problem is well posed, as in the case of the Helmholtz equation. So in this case, they are similar. And again, we have been able to obtain an inner product which is new, which is defined in configuration space, So in the solution of this equation, which is positive definite Hermitian, also non-local like in Helmholtz equation, on the Cauchy surface, sigma. Okay, so using the initial values for the function for the field and the initial values for the normal derivative, we are able to construct a non-local involving a convolution kernel, okay, between this function. Okay, in this case, the geometry is this one. So the momentum of the solution, tachyonic solution, the momentum lie on a one-sheeted hyperboloid, and the one-sheeted hyperboloid is not compact, but shares with the sphere the fact that you need two of them. You need the upper part, which is the future, and the lower part, which is in the past, to describe an arbitrary solution. So you cannot restrict to the positive part, which is positive energy fields, or to the negative part, because this is not Poincare invariant. So you need both of them. And so tachyonic solutions share this feature with Helmholtz solution of Helmholtz equation. Okay. Okay. So
okay,
as in the case,
I just want to remind you of time. So maybe 3 more minutes will be fine.
Okay. So
thank you.
So as in the case of Helmholtz equation, tachyonic solutions of Klein-Gordon equation, they are delocalized. So, and they are delocalized because even though the momentum space is not compact, they cannot take any value. If we project the momentum into the configuration part, into the spatial components, they cannot be the whole R3, but there is a hole here which are not allowed. So there is this hole, and because of the reason you cannot construct a localized solution on the Cauchy surface. Okay, so the solution of this Klein-Gordon equation, they also fails. Okay, so just to finish, give some conclusion. So we see that tachyonic solution of Klein-Gordon equation, they are more similar to Helmholtz solution of Helmholtz equation. So they behave more that like to waves than to particles. So in this sense, you cannot give a particle interpretation to these tachyonic solutions. Okay, so this is the idea essentially. Okay, so just finish just with some reference. Feinberg, the initial paper on fast-light particles. Steinberg and Wolf, they gave a scalar product, a non-local scalar product for Helmholtz equation, and also for reobtaining the scalar product for Klein-Gordon equation. And in this paper, we reobtained the scalar product for Helmholtz equation, and in this last paper, we obtained a scalar product for the tachyon solution of Klein-Gordon equation. And finally, I just give here the scalar product. So if anyone is interested in making an equation, these are convolution. You have double integral on the Cauchy surface. We have a convolution with some kernel, which for the case of Helmholtz equation, the kernel is written in terms of Bessel function of the first kind. The Klein-Gordon equation, the scalar product is 1 with this antilinear expression. Anti-diagonal expression. And the scalar product we obtain for tachyon solution of Klein-Gordon equation is very similar to that of Helmholtz equation, but the kernels in this case, this should be a small, not capital K. The kernel is expressed in terms of Bessel function of the second kind, and this will require some regularization because some of the expression can diverge, so you have to deal with them and take some regularization or interpret them as distributions. Okay, thank you. This is all what I wanted to talk.